All right, let's dive into two words that can be a total headache in math class: domain and range. They might seem a little intimidating, I know, but trust me, by the end of this, you'll see they're not so scary after all.
So I was scrolling through Reddit and found this perfect question. It really gets to the heart of why this topic can be so confusing. You're taught a rule in class, and then you see an example like this that seems to just completely break it. So what is really going on here?
And you know what? The key to solving this whole puzzle is actually pretty simple. It's all about one crucial distinction. The rule isn't actually about the letter x all by itself, it's about the entire expression that's tucked away inside the operation. Let's break that down.
Okay, first things first, let's get back to the absolute basics. Think of a function like a little machine. The domain is just all the stuff you're allowed to put into the machine. Those are your inputs, your x values. And the range, that's everything the machine could possibly spit back out. Your outputs or your y values. That's it. That's the core idea.
All right, now before we even think about getting tangled up in algebra, the easiest, most intuitive way to really get domain and range is to see them. A picture, or in our case a graph, is worth 1,000 equations, for sure.
And there's this awesome analogy from study.com. They call it graph squishing. Seriously, just picture it. To find the domain, you take the entire line of your graph and just squish it flat right down onto the x-axis. And for the range, you guessed it, you do the exact same thing, but you squish it sideways onto the y-axis. So let's give it a shot. If we take this graph here and squish it straight down onto the x-axis, what part gets painted? Well, this red line shows us everything. It starts right at x equals 2, and then it just keeps going to the right forever. So that's our domain. Everything from 2 all the way to positive infinity.
Okay, same idea, but now let's do it for the range. We take this parabola and squish it completely sideways onto the y-axis. You can see, right? The very highest point it ever hits is y equals 5, and from there it goes down and down and down forever. So the range is everything from negative infinity all the way up to 5.
So that squishing method is amazing, right? But what happens when you don't have a graph? Well, that's when you have to fall back on the two non-negotiable golden rules of algebra that really define most domains.
And here they are. Super simple. Rule number 1, you can never divide by 0. It's just a mathematical impossibility. And rule 2, when we're dealing with real numbers, you cannot take the square root, or a fourth root, or any even root of a negative number. These two restrictions are pretty much your main guides for finding the domain.
And boom! This right here solves the whole mystery from the beginning. The rule was never that x can't be negative. The rule is that the stuff inside the square root can't be negative. In this case, that's the 1 minus x squared. So if you plug in a negative number for x, like negative 0.5, you end up with 1 minus 0.25, which is a positive 0.75, and that is totally fine. See? Mystery solved.
Okay, so we've got the fundamentals down, but now let's get into the really good stuff. The common traps where pretty much everyone gets stuck. And these examples come from a fantastic math teacher, Brian McLaughlin, who has seen every mistake in the book. Okay, trap number 1, order of operations. When you see a function like y equals negative x squared plus 4, it's so tempting to do the plus 4 first, shift the graph up 4, and then flip it over. But that gives you the wrong answer. You got to remember your order of operations. That negative sign out front is like a multiplication, a reflection, and multiplication always comes before addition. So you have to reflect the graph first, and then you shift it up.
Oh, and here's another one, a total classic. You see that plus 4 inside the square root, and your brain immediately screams, shift left by 4. But hold on, that's not the whole story here. And the secret? It's always factor first. When you pull that 2 out from the expression on the inside, you're left with square root 2 times x plus 2. And there it is. Suddenly, it's crystal clear. The real horizontal shift is only 2 units to the left, not 4.
You're going to see a pattern here. This next trap with logarithms looks a little different, but the solution is exactly the same. You got to factor first. With log 1 minus x, it's so easy to just guess the shift. But if you rewrite it as negative x plus 1 and then factor that negative sign out front, you get log negative x minus 1. And that tells you everything. It's a reflection over the y-axis, followed by a shift 1 unit to the right.
All right, our final trap is all about rational functions, the ones that look like fractions. Now, when you're simplifying one of these, you might get to cancel a term out. The big mistake is thinking that term just vanishes. It doesn't. It leaves behind a very important clue.
And I love how Brian McLogan describes this. He calls that thing that got divided out a removable discontinuity. But really, for us, it's simpler to just think of it as a literal hole in the graph.
So what does this actually mean? Well, when a term like x plus 1 just cancels out from the top and bottom, it's leaving behind a clue. It's telling you there's a hole in your graph right where x would equal -1. And this is the critical part. That x value is now excluded from the domain, and its matching y value is excluded from the range. The hole messes with both.
Whoa, okay. I know that was a lot to take in. But the good news is we can boil all of this down into a super simple 4-step toolkit that you can use for pretty much any problem.
So here it is, your 4-step game plan. Number 1, see it. If you can, visualize the graph and use the squishing method. Number 2, obey the rules. Always check for division by 0 and even roots of negatives. Number 3, factor first. This is the key to finding the real shifts. And finally, number 4, find the holes. Always, always look for those canceled out terms.
So there you have it. You've got the tools to tackle the domain and range of just about any single function they can throw at you. But what happens when you start plugging one of those function machines inside of another one? Well, that's a whole other story for another time.